Now, in this lecture, we'll find out the length of line segment X using two different methods. In the drawing, we have a semicircle inside a quarter circle. Side AO equals to 6 units. Side AC is tangent to the semicircle at this point. And we want to find out the length of side AC that is equal to X. So we'll start with the first method. And we will define the center of the semicircle as point P. And we will define the point of tendency of tangent AC with this semicircle as point D. Actually, because of the fact that this is a quarter circle, then angle AOB must be equal to 90 degrees. And point O must be the center of the quarter circle. And so here, line segment OA starts from the center of the quarter circle and ends at point A, that is a point on the quarter circle itself. Therefore, line segment AO is the radius of the quarter circle. That is to say, the radius of the quarter circle equals to 6 units. And exactly for the same reason, OB is also the radius of the quarter circle, that is to say, it is equal to 6 units. But OB, it is not only the radius of the quarter circle, but it is also the diameter of the semicircle. And P is the center of the semicircle. O is a point on the semicircle itself. So OP is the radius of the semicircle, and B is point on the semicircle itself. B is point on the semicircle itself, and P is the center of the semicircle. So PB is also the radius of the semicircle. And we know that the diameter of the semicircle equals to 6 units. Therefore, the radius must be equal to half of it. That is to say, the radius must be equal to 3 units. That is to say, OP, that is the radius of the semicircle, will be equal to 3 units. And PV is also the radius of the semicircle, that is equal to 3 units. In the next step, we will join points P and C together by a straight line. So here PC, line segment PC starts from the center of the semicircle, that is to say from point P, and ends at point C, that is a point on the semicircle itself, and this is exactly the definition of the radius. That is to say, PC is the radius of the semicircle, that is equal to 3 units. In the next step, we will join points A and P together by a straight line. And I will present to you a new rule that is actually rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. I will write it down. The lengths of two tangents from a common external point to a circle are equal. So write rule number 1 again. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have point P, point P is an external point in relation to this circle, because point P is not located inside this circle nor on this circle, but it is located outside of this circle. Therefore, point P is defined as an external point of this circle. So if from point P we will draw two tangents to this circle, here the first tangent this is the first tangent. We'll define the point of tendency of the first tangent with this circle as point A. And we'll draw a second tangent to this circle from point P. We define the point of tendency of the second tangent with this circle as point B. And according to rule number 1, the length of two tangents, that is to say the length of the first tangent is PA and the length of the second tangent is PB. So the length of two tangents from a common external point, the common external point is point P, to a circle, 2 points A and B are equal. That is to say PA equals to PB according to rule number 1. Okay, PA equals to PB. So whenever you draw two tangents to a circle from a common external point of that circle, then the lengths of those two tangents will be equal to each other. In this case, PA equals to PB. So actually we can implement rule number 1 in our drawing. Because in our drawing we have the common external point A from the camera start point A, we have two tangents to this semicircle. The first tangent is tangent AO, and the second tangent is tangent AD. And according to rule number 1, the lengths of those two tangents are equal to each other. That is to say, AO equals to AD according to rule number 1. I will write it down. AO equals to AD according to rule number 1. But here AO equals to 6 units according to what is given in the question. So if I write here that AO equals to 6 units, and from this equation 6 equals to AO equals to AD, we will derive that AD is also equals to 6 units. AD equals to 6 units, so here we can write down that AD equals to 6 units. Actually, triangle, the right triangle AOP can point to the right triangle first of all, we will join points P and D together by a straight line. Here PD is the radius of the semicircle because of the fact that line segment PD starts from the center of the semicircle and ends at point D. This is the point of the semicircle itself. For that reason, it is the radius of the semicircle, that is to say, it is equal to 3 units. While PC is not the radius of the semicircle. Why? Because it starts from the center of the semicircle but ends at point C. That is not a point on the semicircle itself, but it is a point on the quarter circle. Therefore, PC is not the radius of the semicircle, that is to say, it is not equal to 3 units. So we delete it. So in the next step, we will prove that the right triangle AOP can point to the right triangle APD. We will prove that the two right green triangles can point to each other according to side rule. I'll write it down. So we prove that the right angle triangle AOP, this right angle triangle, congruent. This is the sign of congruent to the right triangle, the right angle triangle, triangle APD. This right angle triangle and they congruent to each other according to side rule. Okay. So here we know that AO equals to AD equals to 6 units according to rule number 1. AP is a common side that belongs to both triangles, so AP equals to itself. It's a common side that belongs to both triangles. So here AP equals to AP. It's a common side that belongs to both triangles. And finally, OP equals to PD equals to 3 units. It is the radius of the semicircle. OP equals to PD equals to 3 units, which is the radius of the semicircle. So we actually proved that all the sides of the green right triangle AOP congruent to all the sides of the green right triangle APD. Therefore, those two green triangles congruent to each other according to side rule. Triangle AOP congruent to triangle APD according to side rule. And for the fact that those two right angle triangles congruent to each other, we conclude that those two angles are equal to each other. So we conclude that angle OAP is equal to this angle, that is angle PAD. I'll repeat again. From the fact that the two green triangles congruent to each other, we conclude that angle OAP is equal to angle PAD according to the rule that corresponding angles in congruent triangles are equal to each other. Those two green triangles congruent to each other, therefore the two corresponding angles will be equal to each other. That is to say, angle OAP equals to angle PAD. So if we define angle OAP as theta, here angle OAP equals to theta according to our definition. Then from this expression theta equals to angle OAP equals to angle PAD, we will derive that angle PAD is also equals to theta. Here angle PAD is also equals to theta, so if I know that both those two angles are equal to theta, in the next step We focus on the right green triangle AOP. In the right green triangle AOP, we know that tangent theta equals to OP over AO. OP over OA. I repeat again. In the right triangle AOP, the right green triangle, tangent theta equals to OP over OA. OP equals to 3 units and OA equals to 6 units according to what is given us in the question. So in conclusion, we found out that tangent theta equals to 3 over 6. Here we will divide both the numerator and the denominator on this side of the equation by 3, and we will get that tangent theta equals to 1 over 2. That is to say, tangent theta equals to 1/2. Tangent theta equals to 1/2. In the next step, we will join points O and C together by a straight line. By joining the 2 points together by a straight line, we created triangle AOC, and I'll present to you the law of cosines, and we will implement the law of cosines in this triangle AOC. Okay? So, what is the law of cosines? The law of cosines is true in any triangle. So if you have triangle ABC, this is triangle ABC, this could be any triangle. And we know that side AB of triangle ABC equals to A units in its length, side AC equals to B units, and side BC equals to C units in its length, and the angle between side AB and side AC is alpha. Then, so this is the law of cosines. So here in this triangle ABC, according to the law of cosines, we get that C squared equals to a squared plus b squared minus 2 times a times b times cosine alpha. Okay, I'll repeat again. This triangle ABC, that will be any triangle. C squared equals to a squared plus b squared minus 2 times ab times cosine alpha. So we'll implement the law of cosines in triangle AOC. So I'll copy the triangle AOC in this page and we'll implement the law of cosines in this triangle AOC. Side AO equals to 6 units. It is given as the question. AC, side AC equals to X. It is the line segment that we are looking for according to what is given as. Here side AC equals to X according to what is given as the question. I'll repeat again. Side AC equals to X according to what is given as the question. And here side OC, what is the length of side OC? Point O is the center of the quarter circle, and point C is the point on the quarter circle itself, and this is exactly the definition of a radius. That is to say, the length of line segment OC is the radius of the quarter circle that is equal to 6 units. So OC equals to 6 units is the radius of the quarter circle. Angle OAC equals to theta plus theta, that is 2 theta. So this is triangle AOC. We will implement the law of cosines in this triangle AOC. This will be equation number 1. According to the law of cosines, in triangle AOC, OC squared equals to AO squared plus AC squared minus 2 times AO times OC times cosine to theta. Okay, I'll repeat again. In the right triangle AOC, according to the law of cosines, we will get that OC squared equals to AO squared plus AC squared minus 2 times AO times OC times cosine 2 theta. OC equals to 6 units, OC squared will be equal to, therefore OC squared will be equal to 6 squared, that is 36, and it is equal to AO squared. AO equals to 6, so AO squared is 6 squared, it is 36, plus AC squared. AC equals to X, so AC squared is X squared minus 2 times AO is 6 times O. Usually it is times AO times AC, and AC is X times cosine 2 theta. So here we have 36 on both sides of equation number 1, so 36 will get cancelled. So after we cancel 36, in this side of equation number 1 we have 0, that is equals to X squared minus 2 times 6 is minus 12. So this expression in conclusion equals to minus 12x times cosine 2 theta. Here we will add to this equation number 1, 12x cosine 2 theta. And we get that according to equation number 1, x cosine 2 theta equals to x squared will divide this equation number 1 by x. I remind to you that x is the length of side AC. That is to say, it must be a positive number as a length. It can never be equal to 0, and that is the reason that it is allowable to divide the equation number 1 by x, because x can never be equal to 0, it must be a positive number. So here we divide this equation by x, and we get that according to equation number 1. So x will get cancelled here, and we left only with 12 times cosine 2 theta equals to x squared over x is x. So in conclusion, we found out that according to equation number 1, x cosine 2 theta equals to x. So the only thing that is left to do in order to find out the value of line segment x, the line segment that we are looking for, is to find out the value of cosine 2 theta. Okay, so here we have trigonometric identity for cosine 2 theta. According to the following trigonometric identity, cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta repeat again, cosine 2 theta according to this trigonometric identity equals to 1 minus tangent square theta over 1 plus tangent square theta. But we have already found out that tangent theta equals to 1/2. So we can write here that tangent theta equals to 1/2. Now we can substitute tangent theta in this trigonometric identity by 1/2. We'll do it now, and we get that cosine 2 theta equals to 1 minus tangent square theta. If tangent theta equals to 1/2, tangent square theta will be equal to 1/2 squared. So in the numerator we have 1 minus 1/2 squared over 1 plus tangent square theta is 1/2 squared. Okay? And here 1/2 squared is 1/4, so I'll write it down. In conclusion, we found out that cosine 2 theta equals to 1 minus 1/2 squared is 1/4 over 1 plus 1/2 squared is 1/4. Here 1 minus 1/4 is 3/4, and 1 plus 1/4 is 5/4. So here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled, and in conclusion, we found out that cosine 2 theta equals to 3/5. Now we can substitute cosine 2 theta in equation number 1 by 3/5. According to equation number 1, we found out that 12 times cosine 2 theta equals to x. We substitute cosine 2 theta in this equation, equation number 1 by 3/5, and we get that according to equation number 1, 12 times cosine 2 theta is 3/5 equals to x. So x actually equals to, according to equation number 1, to 12 times 3, that is 36 over 5. X equals to 36 over 5. So 36 over 5 is 7.2 units. Okay, so we found out that x, the right segment that we are looking for, is equal to 7.2 units. So here we can write down that x equals to 7.2 units. X that is equal to AC equals to 7.2 units. We finished with the first method. In the next step, I will present to you how to find out the length of line segment AC that is equal to x according to the second method. Okay. In the second method, we use all the things that we already found out in the first method. First of all, the center of the semicircle is at this point, point P. The point of tendency of tangent AC with this semicircle is at point D. This angle equals to 90 degrees. We already found out that OP is the radius of the semicircle that is equal to 3 units. PB is also the radius of the semicircle, and here PD is also the radius of the semicircle that is equal to 3 units. And here we have already proved the triangle AOP can run to triangle APD. Those two triangles can run to each other according to side rule. And those two angles, therefore, from the fact that those two triangles can run to each other, we derive from it that those two angles are equal to each other. So if one angle equals to theta, then the other angle must be equal to theta. Okay, all those things that we've already done, we already did in the first method. So in the next step, we will do different things in the second method. Here we will extend line segment AC, and we will also extend line segment OB by a straight line until they intersect with each other. and we will define the intersection point between the extended line segment AC and the extended line segment OB as point E. Point E is the intersection point of the extended line AC and the extended line segment OB. Okay, so here by this construction we created a new triangle AOE. This is a right triangle because of the fact that this angle equals to 90 degrees, angle OAE equals to 90 degrees. In the right triangle AOE, it is very easy to see from the drawing that AP is angle bisector. Why AP is angle bisector? Because it divides angle OAE into two halves. Each half equals to theta. For that reason, AP is angle bisector of triangle AOE. So we have the angle bisector theorem. According to angle bisector theorem, so if we have triangle ABC that could be any triangle, this is triangle ABC. And here AD is the angle bisector of triangle ABC. AD is the angle bisector of triangle ABC, that is to say, it divides angle BAC into two halves. Each half equals to theta. For that reason, AD is the angle bisector of triangle ABC. According to angle bisector theorem, we get that the angle bisector in a triangle divides the side that it hits. Here I write down in the brackets that in our specific drawing we are relating to AD, that is the angle bisector of triangle ABC. Okay, we are relating to side AD, that is the angle bisector of this triangle ABC. So the angle bisector in a triangle divides the side that it hits in this case, the angle bisector of AD is side BC, so we are relating to side BC. Actually, the angle bisector AD divides side BC into two parts. The first part is BD and the second part is DC. So the angle bisector in a triangle divides the side that it is in a ratio as I already said, here the angle bisector AD divides side BC into two parts, BD and DC. And the ratio between those two parts is BD over DC. So in a ratio that is equal to the ratio between the angles legs. So here we are relating to the angle that has been bisected into two halves, that is to say we are relating to angle BAC. Angle BAC is two legs. The first leg is AB and the second leg is AC. And the ratio between those two legs is AB over AC. So the ratio between the two legs of angle BAC that has been bisected into two halves, that ratio that is AB over AC equals to the ratio that angle bisector AD divides side BC. And the ratio that angle bisector AD divides side BC is BD over DC. So in conclusion, AB over AC, that is the ratio between the angles legs, equals to the ratio that angle bisector AD divides side BC, that is BD over DC. That is to say, AB over AC equals to BD over DC. Okay? I'll repeat again. The angle bisector in a triangle, that is to say, AD, in this case, divides the side that it is. Angle bisector AD is side BC, and it divides it into two parts, BD and DC. And the ratio between those two parts is BD over DC, and that ratio equals to the ratio between the angles legs. We are relating to the angle that has been bisected into two halves, that is to say to angle BAC, and the legs of angle BAC, they are AB and AC, and the ratio between those two legs is AB over AC, and that ratio equals to the ratio that angle bisector AD divides side BC, that is BD over DC. In conclusion, AB over AC equals to BD over DC. That is the angle bisector theorem. So we can implement the angle bisector theorem in our triangle AOE. So we'll copy the right triangle AOE and we will implement the angle bisector theorem in this triangle AOE. side AO equals to 6 units. AP is the angle bisector of triangle AOE. So actually, this is the right triangle AOE that I copied from the original drawing. Here OP is the radius of the semicircle that is equal to 3 units. And AP is the angle bisector of triangle AOE. That is to say, it divides angle OAE into 2 halves. Each half equals to theta. So according to angle bisector theorem, we will get that the angle bisector AP divides the side that is actually side OE, into 2 parts, OP and PE, and the ratio between those 2 parts is OP over PE, and that ratio equals to the ratio between the angle's lengths. We are relating to the angle that has been bisected into 2 halves, since we say they are related to angle OAE. Angle OAE has 2 legs, AO and AE, and the ratio between those 2 legs is AO over AE, and that ratio equals to the ratio that angle bisector AP divides side OE, that is to say it is equal to OP over PE. Okay, conclusion is found out that OP over PE equals to AO over AE according to angle bisector theorem. So here, this is the question number 1. OP equals to 3 units over PE, and it is equal to AO, that is 6 units, over AE. So in conclusion, according to equation number 1, we found out that 3 over PE equals to 6 over AE. Here we will divide this equation by 3, and we will multiply it by AE, and we will get that according to equation number 1, 6 over 3 equals to AE over PE. 6 over 3 is 2. So found out that according to equation number 1, 2 equals to AE over PE. We will multiply this equation number 1 by PE, and we get that according to equation number 1, AE equals to 2 times PE. Okay, AE equals to 2 times PE. So AE is twice as large as PE, and we define PE as A. PE equals to A according to our definition, so we can write here that P equals to A, and also here in the drawing, in the original drawing, we can write down that PE equals to A according to our definition. So according to equation number 1, AE equals to 2 times PE, and P equals to A, so A equals to 2A. We substitute PE by A and we got that A equals to 2A. So here A equals to 2A. Also write here that line segment AE equals to 2A. In the next step, we'll continue to focus on the right triangle AOE and we will implement the Pythagoras theorem on the right triangle AOE. So I'll copy the right triangle AOE in a new page and we'll implement the Pythagoras theorem on the right triangle AOE. A equals to 2A, AO equals to 6, and from the drawing you can see that OE equals to 3 plus A. So here this is the right triangle AOE that I copied from the original drawing. So we will implement the Pythagoras theorem on the right triangle AOE by PT is abbreviation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. This will be equation number 2. Going to equation number 2, the square of the hypotenuse is AE square. And it is equal to the sum of the squares of the perpendiculars, that is to say it is equal to AO square plus OE square. So according to the Pythagoras theorem, in the right triangle AOE, AE square equals to AO square plus OE square. Here AE equals to 2A, so A square is 2A square, and it is equal to AO square. AO equals to 6, so AO square is 6 squared, this is 36, plus OE square. OE equals to 3 plus A, so OE square is 3 plus A squared. So in conclusion, according to equation number 2, we found out that 2A squared equals to 36 plus 3 plus A squared. We will open the brackets on both sides of equation number 2, and we get that 2A squared is 4A squared, and it is equal to 36 plus 3 plus A squared. Here 3 plus a squared equals to 3 squared, that is 9, plus a squared plus 6a. So here, according to equation number 2, 4a squared equals to 36 plus 9 is 45, plus a squared plus 6a. So here we subtract a squared from this equation, equation number 2. And we get that according to equation number 2, 4a squared minus a squared is 3a squared. That is equal to 45 plus 6a. A squared minus a squared is 0. We divide this equation by 3. And we get that according to equation number 2, 3a squared over 3 is a squared. And it is equal to 45 over 3 is 15, plus 6a over 3 is 2a. So in conclusion, we found out that according to equation number 2, a squared equals to 15 plus 2a. Here we will subtract 15 and also 2a from this equation, equation number 2, and we get that a squared minus 2a minus 15 equals to 0. So we have here a quadratic equation, and the missing variable in this quadratic equation is a, and the coefficient a here in this quadratic equation, the coefficient a equals to 1. The coefficient b equals to minus 2, and the coefficient c equals to minus 15, and the variable that we are looking for is a, so x equals to a. And the general formula for to solve a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. So we put the data inside this general formula and we find out the value of the values of a. So here a equals to minus b, b equals to minus 2, so minus b is minus 2, that is plus 2, plus minus square root of b squared. B equals to minus 2, so b squared is minus 2 squared, that is 4, minus 4 times a is 1, times c is minus 15, over 2a. A is 1, so 2 times 1 is 2. So here, actually a equals to 2 plus minus square root of minus 4 times minus 15 is plus 60, and 60 plus 4 is 64. So inside the root what is left is only 64 over 2. So here A equals to 2 plus minus, square root of 64 is 8 over 2. So here we will have two solutions that are possible for A. The first solution for A is that A equals to 2 minus 8 over 2. 2 minus 8 is minus 6. Minus 6 over 2 is minus 3. In conclusion, we found out that according to the first solution for A is equal to minus 3. That is a negative number. While here A, according to our definition, A is the length of side PA. A is the length of side PE. So A is the length, and as a length, it must be a positive number. Okay, A as a length must be a positive number, so it can never be equal to minus 3, that is a negative number. So we cancel this solution and we left only with the second solution, that A is equal to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So we found out that A equals to 5 units according to the second solution. Here we can write down that A equals to 5. If A equals to 5, then 2A is 2 times 5, that is 10. So in conclusion, here AE equals to 10 units, PE equals to 8, that is 5 units. So here, what is the length of BE? The length of line segment BE the length of line segment BE. From the drawing, it is very easy to see that the length of line segment BE is PE minus PB. PE minus PB is the length of line segment BE. I repeat again, BE equals to PE minus PB. PE equals to A, that is 5 units. And PB equals to 3 units, that is the radius of the semicircle. So in conclusion, we found out that BE equals to 5 minus 3, that is 2 units. BE equals to 2 units. Here BE equals to 2 units. And what is the length of line segment CE? The length of line segment CE from the drawing, it is very easy to see that the length of line segment CE, this line segment, it is equal to AE over AC. Again, AE over AC equals to CE. AE minus AC. Again, AE minus AC equals to CE. I'll repeat again. CE equals to AE minus AC. So CE equals to AE equals to 10 units. This is 2A, that is equal to 10 units. AC equals to X. This is the line segment that we are looking for. So in conclusion, we found out that CE equals to 10 minus X. CE equals to 10 minus X. So we can write here that CE equals to 10 minus X. In the next step, we will complete the quarter circle to a circle. So we completed the quarter circle to a circle, and we will extend line segment OB by a straight line until it touches the circle, or until it intersects with the circle. And we will define the touching point of the extended line segment OB in the circle as point M. In the next step, I will and what is the length of line segment OM? The length of line segment OM. O is the center of the quarter circle. M, and it is also the center of the circle itself, of course, and M is a point on the circle itself. This is exactly the definition of the radius. That is to say, OM is the radius of the circle, that is also the radius of the quarter circle. That is to say, OM equals to 6 units. OM is the radius of the quarter circle, that is also the radius of the circle itself, is equal to 6 units. The next step, I will present to you a new rule that is actually rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, then the following equation is true. So here we have the external point, point P, point P is the intersection point between the two chords. So I write it down. Point P is the intersection point. Of the two chords. So we have the first chord is called AB. That intersects with chord CD at point P. Point P is the intersection point. This is called CD. I repeat again. Chord AB intersects with chord CD at point P. Point P is the intersection point of chord AB with chord CD. Therefore, according to rule number 3, we will get that PA times PB equals to PC times PD. I repeat again. If chord AB intersects with chord CD outside the circle as point P is the intersection point between chord AB and chord CD, then according to rule number 3, PA times PB equals to PC times PD. So I read again rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, then the following equation is true, that PA times PB equals to PC times PD. And P is the intersection point of chord AB with chord CD. So we can implement rule number 3 in our drawing. In our drawing, we have chord AC intersects with chord MB at point A. So point A is the intersection point of chord AC with chord MB. I'll repeat again. In our drawing, chord AC intersects with chord MB at point E. Point E is the intersection point of those two chords. Therefore, according to rule number 3, we get that EC times EA equals to EB times EM. repeat again. EC times EA equals to EB times EM according to rule number 3. EC equals to 10 minus X. EA equals to 10 units. And it is equal to EB or B equals to 2 units. Times EM. EM or ME equals to 6 plus 3 plus 3, that is 12. 12 plus 2 is 14. So in conclusion, according to rule number 3, we found out that 10 minus X times 10 equals to 2 times 14. 2 times 14 is 28, so I write it down. So 28 equals to 10 times 10 minus X. Here we'll divide this equation by 10 and we get that according to this equation 10 minus X equals to 28 over 10 is 2.8. Here we'll add X to this equation and we'll subtract 2.8 and we'll get that according to this equation X equals to 10 minus 2.8. 10 minus 2.8 is 7.2. So we found out that X, the line segment that we are looking for, equals to 7.2 units. Okay? X equals to 7.2 units. This is the same result as we found out in the first method. Yeah. The length of line segment AC that is equal to X is equal to 7.2 units. So in the next step I will summarize the lecture. We'll start with the first method. So I repeat on the question of this lecture. We have here in the drawing a semicircle that is inside a quarter circle. We know that side AO equals to 6 units. AC is tangent to the semicircle at point D. And we want to find out the length of line segment AC that is equal to X. So first of all, we defined the center of the semicircle as point P. We defined the point of tendency of tangent AC with this semicircle as point D. And because of the fact that this is a quarter circle, point O must be the center of this quarter circle, and this angle must be equal to 90 degrees. And AO must be equal to the radius of the quarter circle. And we know that AO equals to 6 units, that is to say the radius of the quarter circle equals to 6 units. For the same reason, OB, it is also the radius of the quarter circle, that is also equals to 6 units. But OB, it is not only the radius of the quarter circle, but it is also the diameter of the semicircle. So we know that the diameter of the semicircle equals to 6 units, therefore the radius must be equal to half of it. That is to say, the radius of this semicircle equals to 6 over 2, that is 3 units. So the center of the semicircle is at this point, point P, and O is the point of the semicircle itself. That is to say, OP is the radius of the quarter circle, is the radius of the semicircle. That is to say, it is equal to 3 units. For the same reason, exactly PB is also the radius of the semicircle. That is also equals to 3 units. And for the same reason, exactly, that PD is also the radius of the semicircle. That is to say, it is also equals to 3 units. Then we join together points A and P by a straight line. And I presented to you rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So we have here this circle and we have point P that is the external point of this circle. From point P we draw two tangents to this circle. The first tangent is tangent PA, the second tangent is tangent PB. According to rule number 1, the lengths of those two tangents must be equal to each other. That is to say, PA equals to PB. So whenever you draw two tangents to a circle from a common external point of that circle, then the lengths of those two tangents must be equal to each other. In this case, PA equals to PB. We implemented the rule number 1 in our drawing. In our drawing, we have the common external point, point A. From the common external point, point A, we have two tangents to this circle, tangent to the semicircle, tangent AO and tangent AD. And according to rule number 1, the lengths of those two tangents equal to each other. Here, according to rule number 1, AO equals to AD. But according to what is given as the question, AO equals to 6 units. So we can write here that AO equals to 6 units. And from this equation, 6 equals to AO equals to AD. We will derive that AD is also equals to 6 units. Here, AD equals to 6 units. Then we proved actually that those two right green triangles, triangle AOP and triangle APD, can go into each other according to side rule. I repeat again, we proved that triangle AOP can go into triangle APD according to side rule. So why they can go into each other? First of all, we know that AO equals to AD equals to 6 units. This is according to rule number 1. AP is the common side that belongs to both triangles, so AP equals to itself, and OP equals to PD equals to 3 units. It is the radius of the semicircle. So all the sides of triangle AOP can went correspondingly to all the sides of triangle APD. Therefore, those two green right triangles can go into each other according to side rule. And from the fact that those two right green triangles can go into each other, we conclude that angle OAP equals to angle PAD. We conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two green right triangles can go into each other. Therefore, those two corresponding angles must be equal to each other. That is to say, angle OAP equals to angle PAD. So if angle AOB equals to theta, angle OAP equals to theta according to our definition, from this equation theta equals to angle OAP equals to angle PAD, we will derive that angle PAD, this angle is also equals to theta. So those two angles are both equal to theta. Then we joined points O and C together by a straight line. We created triangle AOC. Then I presented to you the law of cosines, and we implemented the law of cosines in this triangle, triangle AOC. So what is the law of cosines? The law of cosines is true in any triangle. So if we have this triangle, triangle ABC, that could be any triangle, the length from side AB is equal to A units. The length from side AC equals to B units, and the length from side BC equals to C units. And the angle between side AB and side AC is alpha. Then according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times AB times cosine alpha. Okay? And we implemented the law of cosines in triangle AOC according to what is given as the equation AC equals to X. That is the line segment that we are looking for. Angle OAC equals to theta plus theta, that is 2 theta. AO equals to 6 units according to what is given as the equation. And here, side OC of triangle AOC equals to, here O is the center of the quarter circle, C is the point of the quarter circle itself, and this is exactly the definition of a radius. That is to say, OC is the radius of the quarter circle, that is equal to 6 units. So OC equals to 6 units. So here, according to the law of cosines, we will get that OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. Again, OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. OC equals to 6, so OC squared is 6 squared, that is 36, and it is equal to AO squared. AO is 6, so AO squared is 6 squared, that is also 36, minus 2 times AO is 6 times AC is X, times cosine 2 theta. So here we have 36 on both sides of equation number 1, so 46 will get cancelled. And we left only here in this side of equation number 1, we have 0, that is equal to here x squared minus 2 times 6 is minus 12, so this expression equals to, in conclusion, to minus 12x times cosine 2 theta. So in conclusion, we found out that 0 equals to x squared minus 12x times cosine 2 theta. We added to this equation number 1, 12x times cosine 2 theta, and found out that according to equation number 1, x cosine 2 theta equals to x squared. We divided equation number 1 by x, so here x will get cancelled. So according to equation number 1, 12 times cosine 2 theta equals to x squared over x is x. So according to equation number 1, 12 times cosine 2 theta equals to x. So the only thing that is left to do in order to find out the value of line segment x, of the length of line segment x, is to find out the value of cosine 2 theta. Okay, we have trigonometric identity for cosine 2 theta. According to this trigonometric identity, cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. And we have already found out that tangent theta equals to 1 half, so we can substitute tangent theta in this trigonometric identity by 1 half. We did it, and we got that cosine 2 theta equals to 1 minus tangent square theta. Tangent theta equals to 1 half. Therefore, tangent square theta will be equal to 1 half squared. So here, cosine 2 theta equals to 1 minus tangent square theta, that is 1 half squared, over 1 plus tangent square theta, that is 1 half squared. 1 half squared is 1 quarter. Okay, so here we substitute 1 half squared by 1 quarter, and we got that cosine 2 theta equals to 1 minus 1 quarter over 1 plus 1 quarter. 1 minus 1/4 is 3/4, and 1 plus 1/4 is 5/4. So here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled, and we left only with 3/5, or 3/5. So we found out that cosine 2 theta equals to 3/5. Now we can substitute cosine 2 theta in equation number 1 by 3/5. Here, equation number 1, according to equation number 1, 12 times cosine 2 theta equals to x. We substitute cosine 2 theta by 3/5, and we got that, according to equation number 1, 12 times cosine 2 theta is 3/5, and it is equal to x. Here, 12 times 3 is 36, and 36/5 is equal to x. So x equals to 36/5, that is 7.2 units. So here, x that is equal to AC equals to 7.2 units. We finish with the first method, and then I presented to you how to find out the length of side AC that is equal to x according to the second method. In the second method, we used in all the fields that we have already found in the first method. Here this angle equals to 90 degrees, OP equals to PB equals to PD, it is equal to 3 units, that is the radius of the semicircle. We join points A and P together by a straight line, and found out in the first method that those two triangles can go into each other according to side rule. Therefore, those two angles must be equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if one angle equals to theta, then the other angle must be also equal to theta. All those things we have already found out in the first method. Okay, in the second method, we did another construction. We extended line segment AC by a straight line, and we extended line segment OB by a straight line until they intersect with each other at point E. Point E is the intersection point of the extended line segment AC and the extended line segment OB. So in this way, we created the right triangle AOE. In the right triangle AOE, AP is the angle bisector. Why? Because it divides angle OAE into two halves. The first half is theta and the second half is also theta. So what is angle bisector theorem? Angle bisector theorem is that the angle bisector in a triangle divides the side that it hits in a ratio that is equal to the ratio between the angle's legs. So here we have triangle ABC that could be any triangle, and AD is the angle bisector of angle BAC. Why? Because AD divides angle BAC into two halves. Each half equals to theta. For that reason, AD is the angle bisector of triangle ABC. And according to angle bisector theorem, the angle bisector AD divides the side that it hits. Angle bisector AD hits side BC. So we are relating to side BC. And according to angle bisector theorem, the angle bisector AD divides side BC into two parts. The first part is BD and the second part is DC. And the ratio between those two parts is BD over DC. And that ratio is equal to the ratio between the angle's legs. We are relating to the angle that has been bisected into two halves, that is to say we are relating to angle BAC, and the legs of angle BAC are BA and AC, and the ratio between those two legs is BA over AC, or AB over AC. And that ratio equals to the ratio that angle bisector AD divides side BC. That is to say, to BD over DC. So in conclusion, the ratio between the angle's legs, that is actually AB the ratio between the angles legs, that is actually AB over AC, equals to the ratio that angle bisector AD divides side BC, that is actually BD over DC. In conclusion, AB over AC equals to BD over DC. That is the angle bisector theorem. And we implemented the angle bisector theorem in our triangle AOE. Here in the right triangle AOE, AP is the angle bisector. Why? Because it divides angle OE into two halves. Each half equals to theta. So according to angle bisector theorem, the angle bisector AP divides the side that it is side OE, and divides it into two parts, OP and PE. And the ratio between those two parts is OP over PE. And that ratio equals to the ratio between the angles legs. We are relating to the angle OAE that has been bisected into two halves, and the legs of angle OAE is AO and AE. And the ratio between those two legs is AO over AE. So AO over AE equals to the ratio that angle bisector AP divides side OE. That is actually OP over PE. In conclusion, OP over PE equals to OA over AE. Okay? Here OP is the radius of the semicircle that is equal to 3 units. Over PE equals to OA. OA equals to 6 units. According to what is given as the question, over AE. Okay? Here we divided this equation number 1 by 3, and we multiplied by AE, and we got that according to equation number 1, 6 over 3 equals to AE over PE. 6 over 3 is 2, so 2 equals to AE over PE. We multiplied this equation number 1 by PE, and found out that AE equals to 2 times PE, that is to say AE is twice as long as PE. We defined PE as A, here P equals to A according to our definition, and here also PE equals to A according to our definition. So in equation number 1, we have A equals to 2 times PE, we substitute PE by A, and we got that A equals to 2 times PE, that is 2 times A. So according to equation number 1, A equals to 2A. Okay, so here A equals to 2A, O equals to 3 plus A, and AO equals to 6. So I copied the right triangle AOE in a new page, and we implemented the Pythagoras theorem on this right triangle AOE. We have the right triangle AOE here, and according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say AE square equals to AO square plus OE square. AE is 2A, so AE square is 2A square. AO is 6, so AO square is 6 squared, that is 36. OE equals to 3 plus A, so OE square is 3 plus A square. We open the brackets on both sides of this equation number 2, and found out that 2A square is 4A square, and it is equal to 36. 3 plus A square equals to 3 squared, that is 9, plus A square plus 6A. 36 plus 9 is 45. So in conclusion, we found out that 4A square equals to 45 plus A square plus 6A. We subtracted A square from this equation number 2, and found out that 4A square minus A square is 3A square, and it is equal to 45 A square minus A square is 0, plus 6A. We divided this equation number 2 by 3, and we found out that 3A square over 3 is A square, 45 over 3 is 15, and 6A over 3 is 2A. So here we subtracted 15 and also 2A from this equation number 2, And found out that according to equation number 2, a squared minus 2a minus 15 equals to 0. So here we have a quadratic equation. In this quadratic equation, the coefficient a equals to 1, the coefficient b equals to minus 2, and the coefficient c equals to minus 15, and the missing variable in this quadratic equation is a. And the general formula for quadratic equation, for solving a quadratic equation, is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. So here x equals to a, so a equals to minus b. b is minus 2, so minus b is minus 2, that is plus 2, plus minus b squared. b is minus 2, so b squared is minus 2 squared, that is 4, minus 4 times a is 1, and c is minus 15, so it is minus 4 times minus 15 over 2a. a is 1, so 2 times 1 is 2. Here we got that a equals to 2 plus minus. Inside the root we have minus 4 times minus 15 is 60, and 60 plus 4 is 64. So inside the root we left only with 64 over 2. So here we will have two solutions that are possible for a, but first of all a equals to 2 plus minus, the square root of 64 is 8 over 2. So here we will have two solutions that are possible for a. The first solution for a is a equals to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. So we found out that a equals to minus 3, that is a negative number. But here a is the length of side PE, and as a length, a must be a positive number. So a can never be equal to minus 3, that is a negative number. So we cancel this solution, and we left only with the second solution, that a equals to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So we found out that a equals to 5 units. Here a equals to 5 units, therefore 2a will be equal to 2 times 5, that is 10. So a equals to 10 units, and b equals to 5 units. And then what is the length of side BE? From the drawing we can see that BE equals to PE minus PB. B equals to PE minus PB, P equals to 5 units, PB equals to 3 units, this is the radius of the semicircle. So in conclusion, B equals to 3 minus to 5 minus 3, that is 2. Here B equals to 2 units. Then found out the length of line segment CE. From the drawing it is very easy to see that the length of line segment CE is AE minus AC. So CE equals to AE minus AC. AE is 10 and AC is X. So in conclusion, found out that CE equals to 10 minus X. CE equals to 10 minus X. Here, CE equals to 10 minus X. Then we completed the quarter circle to a circle, and we extended line segment VO until it touches the circle at point M. Point M is the touching point of the extended line segment VO in the circle. What is the length of OM? O is the center of the quarter circle. M is the point of the circle itself. And this is exactly the definition of a radius. That is to say, OM is the radius of the circle. That is also the radius of the quarter circle, that is equal to 6 units. Then I presented to you rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, then the following equation is true. So here we have chord AB that intersects with chord CD at point P. Point P is the intersection point. And of those two chords, therefore, according to rule number 3, PA times PB equals to PC times PD. We implemented rule number 3 in our drawing. In our drawing, we have chord AC that intersects with chord MB at point E. Point E is the intersection point of those two chords. Therefore, EC times EA equals to EB times EM. Again, chord AC intersects with chord MB at point E. Therefore, according to rule number 3, EC times EA equals to EB times EM. EC equals to 10 minus X, EA equals to 10, EB equals to 2, and EM equals to, or ME equals to 6 plus 3 plus 3, that is 12. 12 plus 2 is 14, so ME equals to 14 units. So we got the 10 minus X times 10 equals to 2 times 14. 2 times 14 is 28. So in conclusion, we found out that 10 times 10 minus x equals to 28. We divided this equation by 10, and we found out that 10 minus x equals to 28 over 10 is 2.8. Here we added to this equation x, and we subtracted 2.8, and we got that x equals to 10 minus 2.8. 10 minus 2.8, 10 minus 2.8 is equal to 7.2. So we found out that x, the line segment that we are looking for, that is also equals to AC, is equal to 7.2 units. So in both methods, we found out that the length of line segment AC that is equal to x is equal to 7.2 units. Okay? Thank you very much.